Yeah, baby. Uh-huh. We got axes, baby. Yeah. Well, actually, not axes like guitar axes. No. We're talking axis. Axis. Like ECG axis. That's what this is all about. We're going to start a new section now on the ECG axis. Yep, this is Dr. Nick. Welcome to the intermediate section in the ECG Academy's interpretation course to make you an ECG expert. It's easy. Just watch all the videos and let me show you how. So this introductory video is more of a review to help you understand how to figure out the axis of an ECG. We're going to be concentrating mostly on 12 lead tracings now. An axis becomes an important point to make certain diagnoses based on whether there's axis deviation. So let's get started. Remember, the ECG is basically a recording system to pick up differences in electrical activity between 2 points in space. Well, that would be a bipolar recording system, and the ECG machine is basically a voltmeter. Now, true, some leads are more unipolar, the augmented leads, and we'll talk more about that. But remember, what a bipolar recording system does is it detects differences in electrical potential or voltage across 2 different points in space. So let's say you have this cloud of electrical activity, these electrical charges. In the body, of course, the cardiac cells depolarize through their action potential. The cells become more positive on the inside, and this movement of sodium and potassium ions creates this electrical signal. So as the electrical signal moves towards this recording bipole, or basically 2 poles of an electrical recording system, they'll encounter the first electrode, and so now there's a difference in electrical potential between the two. So the machine records a positive deflection. As the signals move across, you might wind up with neutralization of this signal. So now both electrodes are at the same voltage, and the signal drops back down to normal. But as this electrical signal moves further, the signal has a potential for becoming negative before this signal finally goes on by and results in resolution of this electrical squiggle. Okay, so this was covered in the electrical theory and the circuits way back in the beginning of the course, but that's generally how ECG machines operate. So let's get to the real heart of the matter. Ha ha ha. Get it? Heart of the matter. The ECG machines record electrical signals from the limb leads and the precordial leads, which are the ones that we put on the chest wall. We'll cover these in a minute. Now, as far as the color coding is concerned, I had reminded you that if you're driving in the United States and your left arm is hanging out the window, it'll get tanned. So that reminds you that the left arm gets the black electrode. The right arm will not be tanned, and so that gets white. Your right leg is over the gas pedal, so you get green for go, and the left leg would be over the brake pedal, and red would be for stop. Now let's keep in mind that in Europe, the color coding is a bit different. And these are the colors in Europe. The right arm gets red, the left arm gets yellow, the left leg is green, and the right leg gets black. Well, for the time being, let's just stick with the US colors and talk about the different leads and what electrical vector they are pointing to. Lead 1 records electrical differences between the right arm and the left arm. Lead 2 records electrical differences between the right arm and the left leg, and lead 3 records electrical differences between the left arm and the left leg, creating a kind of a triangle which is known as Einthoven's triangle after the fellow who did much of the early work in electrocardiography. The right leg is generally used as a ground just to help eliminate some of the electromagnetic interference that these recording systems can pick up from the outside world. Well, we generally don't think about triangles when we talk about axis. We think of a circle. You'll just have to remember the angles that we talked about. Now, the circle is divided up into 360 degrees, with 0 degrees being defined as this point on the right-hand edge. Lead 1, of course, is pointing toward the 0-degree angle. If the axis is located in this direction, the degrees are expressed as positive degrees. And if the axis points in this direction, then by convention we use negative degrees. Now, if we think of this triangle as covering the entire 360 degrees, we can split this up into 6 equal portions. And we have to do that by drawing lines that are 60 degrees away from the horizontal. So remember, in English at least, we read from left to right and from top down. So lead 2 2 will go in this direction, 60 degrees above the horizontal, while lead 3 will be at this angle, again 60 degrees above the horizontal, thus dividing this circle into 6 equal portions of 60 degrees each. Well, the machine also has 3 augmented limb leads, AVR, AVL, and AVF. And basically what happens in AVL, the left arm is taken as one part of the recording system, and the other pole comes from the other leads, basically summed together. So it's almost sort of kind of unipolar signal, but it's basically looking at signals running towards the left arm. And by convention, we consider AVL to be 30 degrees above the horizontal in this direction. Likewise, AVR is 30 degrees above the horizontal, but pointing towards the right arm. And finally, AVF is basically pointing towards the feet. Well, I had to just fix my lead 2 a little bit to make it look prettier. But that's basically the whole circle. Now, what does axis tell us? It basically tells us what general direction is the electrical signal traveling. So here's the heart inside the guy's chest. And if the electrical signal is traveling in the proper direction, generally what happens is ventricular activation is going to be traveling down and towards the patient's left. As a matter of fact, the atrial signal starts in the high right atrium, and that will generally travel down and towards the left as well. So we usually consider this quadrant here to be the normal area for axis to be in. If the axis winds up being outside of this quadrant, well, there's a little bit of a margin of error. So if it's in this region here, we'll often call it a leftward axis, but it's not a true left axis deviation unless it's greater than minus 30 degrees. This would be minus 30. On the other hand, if the axis is greater than plus 90, we'll call it a rightward axis until it reaches about plus 120, at which point it really does become a right axis deviation. So you have left axis deviation, which is minus 30 degrees or above, and you have right axis deviation, which is plus 120 degrees or higher. Now, how we actually measure axis using the 12-lead ECG is the subject of the next lesson. But before we get to that, I want to mention the precordial leads, because indeed there is a kind of an axis in the precordial leads. Just imagine this yellow oval as being the chest wall with the spine in the back and the sternum in the front. Remember that the heart is attached to the mediastinum at the base, and you've got the pulmonary veins leading into the left atrium, and you've also got the inferior and superior vena cava feeding into the right atrium. The ventricles are clearly lying to the left of the spine in most patients, but because the heart is twisted up, the right ventricle is generally anterior towards the front of the chest, and the left ventricle is more posterior towards the back of the chest. So as the depolarization travels down the septum and towards the apex in 2 directions, you basically have electrical signals that are traveling towards the side of the heart. Now here are the precordial leads and where they're positioned on the chest wall. So if you recall from my earlier talk in the basic section, V1 is recording electrical signals from the front, and most of the signals are going away from V1. And so what you'll usually measure in V1 is sometimes a small R wave, which represents a septal depolarization. If you recall from my basic section. If you don't recall that, you can review that video. But you'll have a little septal R wave and then mostly a deep S wave because the signals are traveling towards the side away from V1. On the other hand, V6, since the septal activation is traveling away from V6, what you usually have is a small Q wave, which is known as the septal Q, but then most of the signal is traveling towards V6, so most of the QRS complex is positive in V6. Somewhere between V3 and V4 is known as the transition point. The transition point is when the R wave grows larger than the S wave, and generally there's a gradual transition across here with V2 having a slightly bigger R wave. V3 sometimes is the transition point, so the R equals S, and sometimes it's V4 where the R becomes taller than the S wave. In V5, there's usually a residual S wave, but by V6, there should be very little S wave left. So you have this gradual R wave transition across the precordium, and we'll talk about abnormalities in this R wave progression in the third lesson in this section. Well, now that we've discussed where the axis comes from, in the next video, we're going to talk about calculating the frontal axis. That's the axis determined by the limb leads, and I'll give you a couple of different ways of doing that. But for now, this is Dr. Nick for the ECG Academy. Thanks for watching.